1. Identify the most acidic proton in the following molecules by indicating their letter. So for this problem, there's a lot of factors we might want to consider, but I'd say the four main ones are charge, hybridization, resonance, and inductive effect. But really, we have to look at each individual molecule to figure out which one applies the most. So let's go down in order. Let's start with the first molecule. We're given four protons, A, B, C, and D. And right off the bat, we notice that protons A and D have resonance structures because there's an adjacent double bond. So this is the bond we're looking at, right? With the alcohol group. And then this is the adjacent double bond. So if this hydrogen atom is removed and turns into a conjugate base, this oxygen will have a negative charge, but then the negative charge can move around. And then this would become a double bond, and this would become a single bond, and the negative charge can move to this oxygen at the top. And remember that resonance hybrids are more stable, so we'll keep A on our radar for now. And then for D, the same sort of thing applies. If we remove this hydrogen atom, this oxygen atom will have a negative charge, but it can be moved around because there's this double bond here. So D also has resonance. In contrast, C and B do not have resonance because there's no adjacent double bond. For B, the closest double bond is here, which is I think 2 bonds removed, so that doesn't have resonance. And the same thing applies to C, where this is a bond, but then there's another bond in between that bond and the double bond, so that's also 2 bonds removed, so we can't have resonance there. So immediately we kind of understand that B and C are probably like less stable conjugate bases, so they would be less acidic protons. In addition, there's a charge on B, but we know that NH3 is ammonia, which is a pretty well-known base, so we keep that in mind. But we're looking back at A and D, and between A and D, the most acidic proton would be A because A belongs to a carboxylic acid group, which has a pKa of around 4 to 5, whereas D only belongs to an alcohol group, which has a pKa of around 16 to 18. And obviously, for when we're considering pKa, the lower the pKa, the more acidic the proton is. So A is the more acidic proton in this case. Now let's move on to the second molecule. This time we're given 3 protons, and we're also asked to identify the most acidic one. So in this case, we know that C does not have resonance because of the same reason specified before. There's 2 bonds removed from the nearest like double or triple bond, so we don't have resonance structure, so that would be the least stable conjugate base, so that would be the least acidic proton, so we're just going to cross off C. Between A and B, these both have resonance structures because there is a double or triple bond adjacent to the bond that the hydrogen is bonded to the carbon with. But in this case, what differentiates A and B is that we need to look at hybridization. A has a more S character because this is a triple bond, whereas B does not have as much S character. And remember, with hybridization, the greater the S character, the more acidic the proton would be because the subsequent conjugate base would be more stable. So in this case, the most acidic proton is also A. Finally, on our third molecule, we're also given 3 protons, and in this case, there's no double bonds to worry about, so there's no resonance to worry about, and there's no charges anywhere. And all of these functional groups, they're all alcohols, so they're all kind of the same. We don't have to worry about that. But if we look closely, we can see these 2 fluorine atoms at the bottom of the ring. And if we recall, fluorine is very electronegative, so there's a lot of these lone pair electrons that are not drawn here, but we know they're there. And in this case, we're just looking for the inductive effect. And all of these alcohol groups do have the inductive effect to some extent, but in this case, since they're all the same groups, we have to look for the one that is closest to these fluorine atoms, because that would mean it's stronger and would be more stable as a conjugate base. So in this case, proton C is the closest to the fluorine atom, so C is the most acidic proton. 2. Provide the products and mechanism, arrow pushing, for the following acid-base reaction. Label the acid base, conjugate acid, and conjugate base. Include all lone pair electrons and formal charges. So I think the first thing we should probably do in this problem is label the acid and base. And in this case, it's pretty easy because if we remember, bases usually are neutral or negative charge, and acids usually have a neutral or positive charge. In this case, this OH would be the base because it's more negative than this neutral molecule here, which would be the acid. And now I guess we could draw in the lone pairs and remember the octet rule. So there's these two bonds, that's basically like 4 electrons. So we're just going to add 4 more, or 2 lone pairs. And then the same with these oxygen atoms over here. And then in this case, since there's only 1 bond from the oxygen to the hydrogen, that would count as 2 electrons, so we need to draw 6 more for a completed octet, or that would be 3 lone pairs. And now we can draw the mechanism and, draw the results, the conjugate acid and conjugate base. If you remember, bases attack or grab the hydrogen atom from the acid, so this negative charge, that's going to be attracted to the quote-unquote proton, or like the H atom on the acid. So this oxygen atom is going to grab the hydrogen, and then this bond over here, it's going to move over to the oxygen atom and become a lone pair. So let's draw the results. This would have a negative charge. This is not very clear. And then this base will become water, H2O. And as you may recall, the acid will turn into a conjugate base, and the base turns into a conjugate acid because it gains a proton. And, the conjugate base loses this proton, this hydrogen atom, so it becomes, or like the acid loses the proton, so then it becomes the conjugate base. 3. Provide the net charge of the peptide shown below at pH equals 7. Indicate which labeled heteroatoms will be protonated, deprotonated, or remain neutral at the given pH. A table of pKa values for several functional groups can be found on the extra resource page. So we're given 4 functional groups in this peptide below, and we want to know what happens to each of the protons in those functional groups at the pH of 7. So I think the first thing we should probably do is label all of the functional groups with their corresponding pKa values. And immediately we see that A and B are the same functional group. They're both amines. And amines have a pKa of about 15. C is a thiol group, which has a pKa of about 7.0. And then D is carboxylic acid, which has a pKa of around 4 to 5. And in this case, we need to remember that if the pH is more acidic, meaning it's less than the pKa of a functional group, then the functional group will gain a proton because it wants to be more acidic and lower its pKa so that it's closer to the pH of 7, which is what we're asked about. So in the case of A and B, because the pKa is 15 and that's greater than the pH of 7, these two functional groups or amines, they will gain a proton. So A and B will have a positive charge, net charge, and will be protonated. C has the same pKa as the pH value, and in this case, nothing happens, so it's going to be a neutral charge. And then for D, since the pKa of 4 to 5 of the carboxylic acid is less than the pH of 7, it wants to become more basic so that the pH or the pKa rises to be more close to 7. So in that case, we're going to lose a proton, so there would be a negative net charge, and then it would be deprotonated. And just to remind you, neutral means there's a zero charge, and we also have to find the net charge of this entire molecule. So we just add up all of the charges. 1 plus 1 minus 1, that would be 1, positive 1. So the net charge would be 1 plus. 4. Label the following molecules as E or Z, and then provide the IUPAC name for compound C on the line provided. So for this problem, we're asked to assign the E and Z configurations, which applies to alkenes. And basically, E means that the higher priority groups are on opposite sides, or they're like diagonal from each other across the alkene. And then Z corresponds to Z same side, or like the same side. So they would be on the same side of the alkene. So I'm just going to write that down. E opposite, and then Z is same. So let's just go down the list of these 4 molecules and assign E and Z to them. So for molecule A, we see this alkene in the middle. We see a chlorine and a methyl group here. And obviously the chlorine is has higher molecular weight than the first atom in the methyl group, which is a carbon. So we're going to circle chlorine as the higher priority atom. And then on this side, we need to fill in for hydrogen, because remember that carbon wants to form 4 bonds, and we don't always draw the hydrogens, but you can in this case to make it easier to see which one's the bigger group. And in this case, it's pretty obvious that the methyl group on the bottom left side is the greater priority group, because hydrogen is the smallest atom on the periodic table. And so in this case, because they're diagonal from each other across the alkene, this would be an E configuration. For molecule B, we have a cyclic alkene, and normally when we name stuff, we don't really assign E and Z to cyclic alkenes, but I guess for this problem, we're asked to anyway, so let's just figure that out. So in this case, we have this alkene here, and then we have this left side, which consists of a methyl group here, and then this big group, which is like the rest of the carbon ring. And obviously, the carbon ring is bigger than the methyl group, so I'm going to circle this top left part of the alkene. And then on the right side of the alkene, the double bond, we want to fill in a hydrogen again, because carbon forms 4 bonds, and this is only 3 bonds. And in this case, same thing applies. It's pretty obvious at this top side, the carbon ring is a bigger substituent, or I would say substituent in quotations, than the hydrogen atom. And so we're circling that. And as you can see, this is kind of like parallel to the alkene bond, and that means they're on the same side. The highest priority substituents are on the same side, so this would be the Z configuration. For molecule C, we might be tripped up at first because there's 2 possible alkenes that they give us. There's this one on the left, then there's this one in the middle, but we're only asked for 1 E or Z configuration, so we need to make sure we choose the right one. So let's just go down from the left and just figure it out. This left alkene, we can't assign E or Z configuration, because if you remember from class, these 2 are both hydrogens, because once we fill in the hydrogens, since carbon wants to form 4 bonds, they're the same. The 2 hydrogens are the same atom. There's no like atoms attached to it, so then you can't really assign E or Z, because they would be the same molecular weight and therefore in like the same priority. So this one, this alkene on the left, we do not care about. So let's look at this alkene in the middle, this double bond. Let's fill in the hydrogen atom on the right side, and this kind of makes it really clear that the bottom part, this group is bigger, and so that's the higher priority group on the right side. But then let's look at the left side, because that's a little bit confusing, because we see that there are 1 and 2 carbon bonds on both sides, but then this one has a double bond and this is a single bond. So let's go ahead and rewrite it as hold on. Let's rewrite it as the atoms, because I think that makes it clearer. That's what I would probably do in this problem. So we know that this is a carbon. The first connection would be a carbon. And then in the top one, there's one hydrogen. I'm just drawing an arrow to show that it goes this way. But on the bottom, there's 2 hydrogens. And then for the top, there's a carbon after this hydrogen. And we can just kind of go down the list. So carbon, carbon, they're the same. We can't assign E and Z to those. Hydrogen and hydrogen are also the same. But then in this case, the carbon and the hydrogen are different. And obviously carbon has a greater molecular weight than hydrogen. So in this case, the higher priorities group would be this top part would be double bond. So in this case, because the alkene or the double bond in question is this one, and these two groups, these high priority groups, are diagonal from each other, they're in opposite sides, so this would be an E configuration. For D, molecule D, we're asked again about a cyclic alkane this time. And there's also 2 double bonds, but just remember, don't get tripped up by this, because we can't assign E and Z configuration to this double bond since it's connected to an oxygen, not a carbon. So let's just kind of like get rid of that for now. So we're looking at this bond, and in this bond, we can kind of just apply the same logic we did for this one, where we just go down the atoms in a list. So this left side, there's carbon, and then there's another carbon. It's carbon here, and then there's a second carbon, and then here there's a third carbon. But then on this side, there's no additional amine group, so this would be, this top left side would be the greater molecular weight, would be the higher priority substituent on that side. And then on the right side, we kind of know that this is, this carboxylic acid is higher priority or has greater molecular weight because of this oxygen atom, which adds a lot more weight than this side, which just has 1 oxygen atom, whereas this top part has 2. So, and we can see that these 2 groups are parallel to the bond that's drawn here, and that means that they're on the same side, so that's a Z configuration. Now let's answer the other part of the question, which asks us for the name of compound C, which is this compound right here. And I'm just gonna erase these markings so that it's easier to see. Like I mentioned before, when we were determining the E and Z configurations of these molecules, since C only has 1 alkene that actually does have an E or Z configuration, we do not have to number them. But in this case, we still do have to number the parent chain as always, and there's kind of 2 ways to do it. We can either go from 1 starting on the left and then going to the right, or we can start from the right and go to the left. And we want to go from the left to the right because, as you can see, these 2 double bonds or alkenes are concentrated on the left side of this molecule, and so we want them to have the lowest numbers possible. So we're going to start from the left. So this would be 1, 2, 3, 4, 5, and then 6. So we see this as a 6 carbon parent chain. And like I mentioned before, since only this alkene actually has E or Z configuration, we don't have to write 3E, we can just write E. So I'm going to do that. But you can write 3E and you'll get full credit, but I just think it's simpler to just keep it at E. And then the next thing we want to do is order the substituents in alphabetical order. So these are two methyl groups, and then this is an ethyl group. And obviously E comes before M in the alphabet. So we're gonna write 3-ethyl first. And then since there's two methyl groups here, that's 5,5-dimethyl. And then we have to account for the alkenes. There's an alkene at number 1, and then there's one at number 3. So we would write 1, 3, and then hexadiene, because hexa for the 6-carbon long parent chain, di for the 2 alkenes in the molecule, and then ene is the ending because it's an alkene and not an alkane, not an alkyne. 5. Give the major products of the following reactions. Draw all stereoisomers produced in the reaction. Also indicate whether the products are enantiomers, E, diastereomers, D, achiral, A, or a chiral single product, SP. Note, providing mechanisms is not required for full credit, but can be used in assigning partial credit if the correct product is not shown. So for this problem, I think I'm just going to go in the clockwise fashion, starting from the reaction with HBr, and I'm going to draw out the mechanism so that it's easier to understand. So we have this molecule, and we're reacting it with HBr, which kind of looks like this. HBr is kind of like that, and then if you remember, this double bond will grab the hydrogen, and then this bond will disassociate and then produce a negative bromine ion. So then the next molecule that results in this reaction mechanism would be like this. And keep in mind there's two possible places you can place the carbocation. It can either be here or it can be here, because they're both of these carbons are in between this double bond. But we want to put the carbocation on this carbon because it's attached to 2 other carbons, making it secondary, and it's more stable than this one, which it only immediately has one neighboring carbon, which makes it primary and less stable. And in this case, there's no rearrangement, because even though we have this methyl group, it's 2 carbons apart and not just 1 carbon apart, so we cannot shift it. And the next step would be to take the negative bromine ion, and react it with the carbocation. And because there's no hindrance from either side of this carbocation, we're going to have 2 products, and it's going to be a racemic mixture. So this bromine ion will attack this carbocation, and then we will get a product like this. But because all of these substituents are different, remember this is also a hydrogen atom attached to this carbon. This side is different from this, and then the bromine, the hydrogen, they're all different substituents. So we can't just leave it as a line, we have to draw a wedge and a dash. We could draw it like this, which kind of indicates that it's a racemic mixture of both, but this problem specifically asks us to draw all the products. So we want to draw both the wedges and the dashed versions, like this. So I'll just draw it in. Sorry, this is getting kind of hard to fit. And keep in mind that we do not change anything here. We don't change these dashes into a wedge or anything like that because it's so far from the reaction site, which is here, that it doesn't participate in the reaction. And if it was participating, it would be different, but since it's not participating, we just leave it as dash. And now we can determine whether it's an enantiomer product, diastereomers, achiral, or a chiral single product. In this case, these are diastereomers because the definition of a diastereomer is that not all of the stereochemistry is changed. So in the case, if these were enantiomers, these would both be dashes, and then these would both be wedges. But that's not the case. So these are diastereomers. It's also not achiral or a chiral single product. It's not a chiral single product because obviously the bromine ion can attack from both sides equally since there's no hindrance. So we get two major products that are equal. I'll just write that here. So it's not a chiral single product. And also it's not achiral because as you can see, it's not a meso compound, and then there's like multiple chiral centers here and here, so it's not achiral. So it's a diastereomer. Going in the clockwise order, the next reaction we're going to be looking at is hydroboration oxidation, which is this one, and it's a little bit more complicated, so I've prepared another sheet to explain the mechanism. So the first step in this reaction mechanism is the hydroboration step. So we have our original molecule, which looks like this, and we're reacting it with BH3, which kind of just looks like H bonded to another BH because BH2 because that's how it's better represented for the reaction. And in this case, it's a syn addition because this alkene, this double bond, and then this BH3 or HBH2 is gonna both react on this side. So this bond between the hydrogen and the boron will grab this side of the double bond, and then the other side will go back to the boron atom. And this will result in a molecule that looks like this. The next step, here I'll label these. The next step in this reaction mechanism is an acid-base deprotonation. So remember we have the NaOH, which is an ionic bond, so it dissociates into Na plus and OH minus, and keep in mind that the negative charge is on the oxygen and not on the hydrogen. And in this case, the disassociated OH minus ion will grab onto this hydrogen from the H2O2, and then this other bond will disassociate and dump its lone pair electrons on the oxygen next to it. And then you'll have a water atom and OOH with a negative charge on one of the oxygen atoms. And then the third step in this mechanism would be that the OOH minus attacks the boron from this byproduct up at the beginning. And technically it's going to be NaOOH, but since it's an ionic bond, we don't really care about the Na plus. We kind of just care about this negative anion. So I'm just going to redraw this molecule. You don't have to draw this hydrogen atom, but I am drawing it just for clarity purposes. So this OOH minus will attack this boron, and you'll get something like this. And keep in mind that this oxygen, this OOH, is not attached to this carbon. it's attached to this boron, and that's really important. And throughout this mechanism, this methyl group, this dash methyl group is not participating, so we just continue drawing it with a dash. The fourth step in this reaction mechanism is that the carbon-boron bond, so this bond right here, is going to migrate to bond to this oxygen instead. So I'll draw that out. And then because we always have, whenever we push an arrow somewhere, there's going to be an opposite arrow pushing out of it. So in this case, we're going to have to disassociate this bond, and then this will give us a product like this. And then we'll have a byproduct of OH minus coming from this OH that's leaving this molecule. So basically, the BH2 and the O, the oxygen atom, just kind of switch places. The fifth step in this reaction mechanism is that the OH minus from the previous this byproduct, this hydroxide ion, is going to attack the BH2. So I'm just going to draw it out again. Sorry, I keep forgetting that we switched the places of the oxygen and the boron atom. And remember that it's always the negatively charged ion that attacks the other thing. It's not the positive one, it's the negative one. So it's going to attack the boron. And of course, we always have to have an opposite reaction. So this bond right here is going to disassociate into lone pairs. And then we'll have a product that looks like this. And a byproduct of BH2OH, which comes from this hydroxide ion reacting with the BH2. And at this point, the oxygen, this oxygen anion is unstable because remember that molecules or atoms always want to achieve the most neutral charge they can have because it means greater stability. So in this case, it wants to stabilize. And if you remember from one of the first steps we went over, there's a water atom that came as a byproduct in one of the reactions. So we're going to bring that water atom back, a water molecule back, and it's going to act as an acid and donate a proton or a hydrogen atom to this oxygen anion, which wants to stabilize. And it'll gain a neutral charge, which is more stable than a negative or positive charge. So the reaction looks kind of like this. This is the water atom molecule, sorry. And this, remember that it's always the negative, the atom carrying the negative charge is the atom that attacks, in quotations, the other molecule. So in this case, this negative oxygen, it's very electronegative, and so it's going to be attracted to this hydrogen, and then we always have to do another arrow showing that this bond is being broken, this bond. So we'll get something like this. And then we'll have an OH minus again, which, if you remember, there's an positive sodium ion, so it's just going to be like NaOH, but we don't really care about that because it's not really the molecule that we care about. So going back to this page, the product is a single product, and it's this one. You can draw it as this without the hydrogen atom here, because remember that for carbon skeletons, we don't have to include the hydrogen atoms because they're just assumed to be there and bonded to the carbons. As you can see here, this is a single product, and it doesn't have stereochemistry for the reaction site, which is this carbon, because, like I said, in a carbon skeleton structure, there's always going to be assumed to be hydrogens attached to the carbons when they're not shown. So in this case, there's going to be two of them, and because they're the same atom, both of the hydrogens are the same atom, we don't assign stereochemistry. So this is going to be a chiral single product. It's not achiral because obviously it's not a meso compound, and also there's this chiral center right here, but it will be a single product, so it's going to be a chiral single product. It also isn't going to be a diastereomer or enantiomer because obviously we only have one product, so we can't really assign that. And you can kind of think of it as an anti-Markovnikov reaction or addition of an alcohol because the OH group is being added to the carbon in between the double bond, the original double bond, that is less substituted, which is this one, because this is a primary carbon, right? It only has this as a neighboring carbon, and then there's two others that are just hydrogens. But then this carbon right here, it has one carbon and another carbon attached to it, making it a secondary carbon. So we want to remember that in the hydroboration oxidation reaction, it's an anti-Markovnikov addition of an alcohol, if you remember nothing else. The third reaction we're going to be looking at for this molecule is its reaction with Br2, and this is a lot simpler than the previous one, so that's good, but I'm still going to draw out the mechanism so that it makes more sense. So we're starting off with this molecule, and we have this Br2, which I'm going to represent with Br, and then a line in between to connect to the other bromine atom, which signifies the bond. And as always, this double bond is going to go and attack and grab onto this bromine atom, and then this bond will disassociate, and you'll be left with this molecule, carbocation, and then you'll have a Br minus ion. And keep in mind that whenever you are drawing out these reaction mechanisms, a good way to check that you're doing it right is if in the next step, all of the charges add up to the same charge, the same net charge of the previous step. So like in this case, this first step, everything is neutral, right? So it's a net charge of 0. And in the second step, we have a positive molecule and a negative ion. But overall, -1 plus 1 would be 0, so it's a net charge of 0. It's neutral. So that's a good way to check. And I'm just going to move this over. The next thing we want to keep in mind, which is different from the reaction with HBr, is that rather than just straight up attacking this carbocation, or rather than straight up having this bromine ion attack this carbocation, there's another step. And it's because this bromine atom over here on this molecule is highly electronegative, so it's attracted to this carbocation because this has a partial negative charge and it's attracted to this positive charge. So what it's going to do is it's going to try to bind to this carbocation, and you'll have a molecule like this. Positive charge is going to be transferred to the bromonium ion, which basically means a positive bromine ion. And keep in mind that technically this double bond can also be on the other side, like it could be like this as well. So we can also draw another intermediate where there's this bromine triangle thing at the top of the molecule. And then we still have this negative ion, and it's going to attack the more substituted carbon, which is this one. And since it's hindered on this side for this molecule, for this intermediate, the bottom side is hindered. So it's going to attack the top side because there's more space for it to do so. And then as always, if you draw one arrow, you have to draw another one. So this will attack this carbon atom, and then this bond is going to be broken, and the electrons will go back to the bromine. So you're left with a molecule where you have a bromine that is dashed from this reaction. It's grabbing it, and then because this bond is disassociating, we have the other bromine that's going to be here. And keep in mind, this one is not going to be wedged or dashed because it's a carbon skeleton representation, and carbon has 4 bonds, and these are, if you draw them in, there's 2 hydrogens that aren't shown, but since they're the same atom, we can't assign stereochemistry for this one, for this carbon, but we can for this carbon. And then likewise, for this other intermediate product, we can do the same thing, but because this time it's hindered from the top side, this negative bromine ion is going to attack the more substituted carbon from the bottom side. So we're going to have a wedged bromine here. And then the rightmost bromine atom is still going to be the same. It's not going to have stereochemistry because, like I said, there's 2 hydrogen atoms that are bonded to this carbon that the bromine is bonded to, so we can't really assign it since both of the hydrogens are the same atom, they're the same molecular weight. So we're going to have these 2 as the products, and I'll redraw it in a moment, but let's consider if they're enantiomers, diastereomers, achiral, or a chiral single product. So obviously it's not a single product, right? Because we have this bromine that is both wedged and dashed, so we can cross that off. It's not achiral because obviously we have a chiral center here and here, so we cross that off. It is not an enantiomer because this methyl group on the left side is not participating in the reaction, just like it wasn't participating in the previous 2 reactions we looked at. So it's going to stay dashed and not change. So what we're left with is that these are diastereomers. So D. And I'm just going to redraw it and make it a little cleaner. But the 2 products that you will get are these 2. Just another note, these 2 products that we get from the Br2 reaction are also racemic, so there's an equal mixture of both. Because keep in mind that this pi bond or this double bond is 3D, so the bromonium triangle ion thing can be either formed on the top of the pi bond or the bottom. So there's not like a reason for one of them to be formed over the other, so they're going to be produced in equal amounts. The final reaction we're going to be looking at in this table of reactions is this molecule's reaction with water and sulfuric acid. Sulfuric acid is a very strong acid, so we can just kind of regard this as a bunch of protons or hydrogen atoms. So the first step of this reaction mechanism will look like this, where this double bond will grab onto this proton, and you'll get something like this. The carbocation can either be here or here, but we're going to put the hydrogen atom on this carbon, this rightmost carbon, because it's less substituted carbon, and the more substituted a carbon is, the more stable it will be as a carbocation. So this carbon atom on the left side of the double bond will be more stable as a carbocation, so we're going to place it there. Then the next step in this reaction is we're going to take this water molecule, and remember that even though the water molecule is neutrally charged, the oxygen atom has a partial negative charge, and it's pretty obvious when you draw in the lone pairs of electrons. There's more electronegativity here. So it's going to be attracted to this positive charge on the carbocation, and it's going to latch onto it and yield something like this. And remember that the charges will always be the same from one step to the next, as long as there's nothing else being added. So rather than just removing this positive charge on the carbocation, it's going to be transferred over to the oxygen atom. I'm just going to move this a little bit. After this step, we still have a bunch of other water molecules in the solution. So another water molecule is going to, this oxygen atom in the center of the water molecule, which has lone pairs and greater electronegativity, it's going to want to grab onto one of these hydrogen atoms, and then this bond will disassociate and dump its lone pairs of electrons onto the oxygen atom. And as a result, we'll get, this is not, there is not a lot of space on this paper. But as a result, we'll get a molecule that looks like this. And in addition, we'll have H3O plus, because remember that this other water molecule is going to gain a proton, and then this water molecule that's added to this original molecule, it's going to lose one and be deprotonated to an alcohol group. So we'll get a product like this. But there are technically multiple products, because I didn't draw the stereochemistry in this mechanism, but there will be stereochemistry, because as you see here in this step, technically the carbocation is 3D, so the atom is 3D. This water molecule can grab onto the carbocation from this bottom side or from this top side, so we're going to have a result where we have an equal mixture of RNS stereochemistry for the alcohol group. So this would be our product, but as we know, this problem wants us to draw all products and not just the hybrid, or which is represented by this sort of zigzag line. So we're going to draw both of them, and remember it's racemic because there's nothing hindering the water molecule from grabbing onto the carbocation. There's nothing that's selectively choosing one side over the other, so it's going to be a 50-50 mix of both products. So they're both going to be major products, which is what this question is asking us for. So I'm going to go ahead and draw that. And as you can see, compared to this other alcohol reaction that yields an alcohol that we did previously, which was, if you remember, this is an anti-Markovnikov reaction, because we have two possible places that the alcohol group can be added from this alkene. It can be here or it can be here, and it's added to the less substituted carbon in this case, which means it's anti-Markovnikov. But in this case, it's added to the more substituted carbon in between the double bond, so this is a Markovnikov reaction. And finally, we have to consider whether these are enantiomers, diastereomers, achiral, or a chiral single product. It's obviously not a single product, so we can cross that off. It's obviously not achiral because we see this these dashes and wedges in both of these major products, which indicates chirality. They're not enantiomers because, as we've seen with all these previous reactions, this methyl group on the left side is not participating, so it stays the same, whereas this alcohol group on the right side of the molecule is participating, and since there's no selection, there's no favorable selection for one side over the other, it's gonna change. The RNS stereochemistry is gonna be different. But since the methyl group on the left side remains the same, we only have one thing changing, so these are gonna be diastereomers. 6. Provide a mechanism for the chlorination of 1,2 dimethyl cyclohexene. Draw the structures of the starting material, intermediates, and products with stereochemistry indicated. Include all lone pair electrons, formal charges, and curved arrows to show the flow of electrons. Note, you only need to draw a single stereoisomer for intermediates, but draw all stereoisomers of the products generated in this reaction. So if you remember from the previous problem, this is really similar to the reaction with Br2, but it's just instead of Br, it's Cl or chlorine. And we're asked to draw in all the lone pair electrons and formal charges. So I guess the first thing we should probably do is draw in the lone pairs for this molecule, the Cl2 molecule. And as always, the double bond is going to act as the nucleophile, and it's going to grab onto this chlorine atom, and then this double bond is going to break, and then the other chlorine atom will become a leaving group. So you're going to end up with something similar to this. And there's going to be a carbocation up here. You can also draw it the other way around, but it really doesn't matter for now because we're asked to only draw a single stereoisomer for the intermediates. And in addition to this molecule, we're also left with Cl- ion because remember that it's a leaving group. And a good way to check that we did this first step right is to check the net charges of each precursor, each intermediate, and the precursor molecule. So this precursor, or these two precursors, they have a net charge of 0 because they're both neutral, right? And then here, both of these are +1 and -1 charge, and that adds up to 0 as well. So that's just a good way to check. The next step is we're just gonna disregard this negative chlorine ion for now, because keep in mind that you don't want to make the mistake of just taking it and adding it here, because that's wrong. The next step actually will be like the formation of sort of a ring where this chlorine atom that's wedged is really attracted to this carbocation because this is highly electronegative. So it's going to take a lone pair and it's going to try to bond with this, which will give us another intermediate that looks like this. And as always, because the charges have to match up in each step, we can't just get rid of the positive charge on the carbocation, and instead it's just shifted to this chlorine. So then it becomes a chloronium ion. And I'm gonna make all of this a bit smaller so we can fit in the next step. So this is the precursor we have now, right? But we have to keep in mind that this precursor negatively charged chlorine atom, it can either attack from this side or from this side, from the top or the bottom, to break one of these wedged bonds, because both this carbon and this carbon are both equally substituted. So there's no preference for either one of them. So we will have two products that are a racemic mixture in the end. And I'm going to just draw out both of these mechanisms so that it's easier to see. But the problem says that you don't have to. You only need to draw a single stereoisomer for intermediates, but I'm going to draw it out anyways. So the first possibility is you take this intermediate with the wedged chloronium ion and this dashed methyl group, and you take this negatively charged chlorine atom, and it's going to it's gonna attack from the top side, and then as a result, this wedge bond is gonna break, and it's gonna dump its electrons back to this chloronium ion, making it a neutral leaving group, and you'll get something like this. And this will be one of your products, and it's going to account for 50% of your products. The second way this might happen, this reaction might occur, is that this same precursor molecule with the wedged bonds with the positive chloronium ion is gonna the negative chlorine leaving group from the beginning is gonna attack from the bottom side, and then this bottom wedged bond will break, and then the electrons will go back to the chloronium ion and make it neutral charge. And as a result, because this negative chlorine ion is grabbing this bottom, it's attacking this bottom carbon, it's gonna push this out. It's gonna push this wedged bond out, and then it's gonna, as a result, also push this dashed bond out and turn this dashed methyl group into a wedged methyl group. And this is why we'll have two different products. And so it's going to end up looking like this. And this will also account for another 50% of the total product that you get in this reaction. So the final products will be a mixture of both of these, and you do have to include both in the products, even though we weren't asked to specifically include both as intermediates. So I'm just going to draw it in. And we were also asked to keep the lone pairs intact, so I'm just keeping that in mind as well. And so that's our final answer. 7. Give the reagents that will complete the following transformations. Please use the letter codes from the reaction menu on the supplemental page above the reaction arrow to indicate your choice. So because depending on the professor and the year or the term you're taking this course, you might not be given a reaction menu. We're just gonna disregard that and just actually choose the actual reagents in this case. And I'm gonna split this into 3 parts, A, B, and C, and I'll identify which reagent it is that's allowing these transformations to take place, and then I'll provide the mechanism and explain it. So for part A, we're given this original molecule, and we see this product molecule where the alcohol is is added to the more substituted carbon, whereas the bromine is added to the less substituted carbon. In this case, the reagents will be Br2 and H2O, and I'll explain why. So we're starting off with this molecule, with this alkene, and we immediately start with the bromine, the dibromide, and as we remember from the previous problems, the alkene acts like a nucleophile and attacks one of these bromine atoms, and then this other one will leave the bond, and you'll have something like this. And you'll also have a negative bromine ion as a byproduct. Then there's going to be a ring formation where this bromine on this molecule is highly electronegative because of its lone pairs. So it's attracted to the carbocation on the left of it, and it's going to try to bond with it. So you'll get something like this. And we can't just ignore the positive charge on the carbocation, but instead it's transferred to the bromine, making it a bromonium ion. And in this case, we want to look at the other reagent that we're given, which is water, and it has an oxygen with 2 lone pairs. And technically, it can either attack this carbon or this carbon to allow one of these bonds to the bromonium ion to break, but it's going to want to attack this more substituted one that's in the middle because it has a greater partial positive charge. And water, which has an oxygen atom, which is highly electronegative, is attracted to that positive charge. So it's going to attack this middle carbon. And then as a result, this bond that is on top of it will break, and the electrons will be dumped and become lone pairs on the bromine atom. And you'll get something like this. Wait a second. I skipped a step. Now you get something like this, where the positive charge is on the oxygen atom. And because it's still positive and not neutral, it's unstable, so it's going to undergo another step of the reaction. And because we have so many water molecules in the solution, we're going to take another water molecule and just react it with this water molecule that's bonded to this molecule. I'll just draw it out again. And in this case, the oxygen atom is going to attack one of these hydrogens, and then this bond will break and dump its electrons onto the oxygen atom on this molecule, and then it's going to make it neutral, so it's more stable. So you end up with something like this, with a byproduct of H3O+. And that's how we get this product. Keep in mind, I didn't draw stereochemistry in this reaction mechanism because I don't think it's necessary to identify the reagents in this case, but you can for extra practice. And I have done so in some previous problems where it was more necessary to do so. For the second part of this problem, part B, we are getting a result that has the alcohol group that's added to the more substituted carbon in between this double bond, which is this carbon. So that means it's a Markovnikov addition, and I'm just going to write that here. And in this case, because it's a Markovnikov addition of just an alcohol group and nothing else, that's characteristic of the reaction with water and sulfuric acid. And I will show you the mechanism. I'm just going to erase the previous one. So we're starting off with this molecule, which is the same for all 3 parts of the problem. And first, we got to remember that sulfuric acid, H2SO4, is a strong acid, so it disassociates in solution pretty rapidly. So we can just regard them as positive hydrogen protons. And we always know that the double bond acts like a nucleophile, so it's going to grab onto this hydrogen, and you're going to get something like this, where the carbocation is placed in the middle carbon because it's more substituted, and therefore it's a more stable carbocation than if you had placed it here. The next thing that's going to happen is we're going to go back to the other reagent, which is water, and water is going to react with this carbocation. This oxygen atom has a lot of lone pairs, so it's highly electronegative, and it wants to bond with the carbocation, so it's going to do that, and you'll get some intermediate that looks like this, with the positive charge transferred to the oxygen atom. And then again, remember that in the solution, there's like millions and billions and trillions of water molecules. So we're going to take another water molecule to make this oxygen atom neutral. And in this case, the water molecule is the oxygen atom on the water molecule is gonna attack a hydrogen, and then this bond will break, and you'll get a result that looks like this. And obviously you'll get H3O plus as a byproduct as well. And again, I didn't draw stereochemistry because it's not particularly necessary for this problem, since you're not really asked to show the mechanism, you just have to be able to identify which reagents you want to use. And that's how I got these reagents, water and sulfuric acid for part B. For part C, we get these molecules as the products, and immediately this is different from the previous part B, in that instead of being Markovnikov addition of the alcohol or OH group, it's an anti-Markovnikov addition because the alkene was originally here, and this was the less substituted carbon, whereas this is the more substituted carbon. And as you can see in both of these products, the alcohol group is added to the less substituted carbon. So it's going to be an anti-Markovnikov addition of an OH group, and that's pretty characteristic of the reaction with BH3 and H2O2 and NaOH. The mechanism for part C of this problem is a little more convoluted, and I have drawn it before in problem 5, but I'll do it again to show you how to get to the products, which are these two. So to start off, we have the same precursor molecule, which is this alkene. Just going to draw a bit smaller. And we start with the BH3 as a reagent. And I'm going to represent it as a hydrogen atom bonded to BH2 because it's easier to show the bonding of the alkene to this molecule. And it's going to be a syn addition, which means that both the hydrogen and the BH2 are added to the same side of this alkene, and the hydrogen is going to grab onto the more substituted carbon on in between this alkene, while the this BH2 group is going to bond to the less substituted carbon, like this, and you'll get an intermediate that looks like this. And technically, the hydrogen and the BH2 are on the same side, so it could be wedged. They're both wedged or they're both dashed, but I don't really think that stereochemistry is necessary for the intermediates in this case, so we're just going to move on. The next thing is that, remember, we also have the NaOH in the solution, and because this is an ionic compound, it's just going to dissociate into hydroxide ions. We also have H2O2, which I'm going to represent as HOOH, and this negative hydroxide ion is going to grab onto one of these hydrogens, and then this bond will break, which will form water and a negatively charged OOH ion. The next step in this reaction is this negatively charged OOH is going to take this molecule, this intermediate, and it's going to bind to the boron. And it's going to give a result that looks like this. And you'll see why I'm separating one of the oxygens from the other hydroxyl group in a second. And because boron is having another bond, the negative charge is going to be transferred onto it. Next, what happens is that this oxygen and this boron switch places in a sort of bond shift mechanism where this bond between the carbon and the BH2 group is going to grab onto this oxygen, and then this hydroxyl group is going to break off and form hydroxide, which is negative. So you'll get a molecule, an intermediate, that looks like this. And you'll have a byproduct of hydroxide ion. Next, we have to consider that we have like a ton of these hydroxide ions in a solution because there's like trillions of NaOH molecules. So the next part of this reaction mechanism is the hydroxide ions in the solution are going to bind to the boron, the BH2, and then this will break the bond between the oxygen and the BH2, and you'll get a negative oxygen atom over here on this top side of the molecule, and a byproduct of BH2OH, which we don't care about because it doesn't really come back up in this reaction mechanism. But now we see that this intermediate with the negative oxygen is not stable because it wants to form a more neutral charge to gain stability. And we also know that above we made water as a byproduct earlier, so that's going to help us in this next part of the reaction where this negative oxygen atom is going to act like a nucleophile, and it's going to grab onto this hydrogen, or it's going to act as a base, and it's going to grab onto this hydrogen, and this water molecule is going to act like an acid, and then subsequently this bond will be broken, and you'll get a more stable alcohol that looks like this, and you'll also have a hydroxide, which is negative, and that's just a byproduct. We don't really care about it, but this is the final product that you will get. And just as another note, this is negative, and remember that Na plus exists in the solution, so it's going to bond to that and become NaOH. But that's how you'll get a product that looks like this. The only thing is that these show stereochemistry, but as I explained earlier, the reason why both the OH and the H that are on both of these equally racemic products are either the same, they're both wedged or they're both dashed, they have the same stereochemistry, is because of this first step that involves syn addition, which means that they're added to the same side of the alkene. 8. Consider which of the following carbocation intermediates will undergo rearrangement. For those that undergo rearrangement, draw the rearranged intermediate. For intermediates that are not predicted to rearrange, write NA. For this problem, I'm just going to go from left to right, starting with this carbocation. And in this carbocation, we have two hydrogen atoms on this neighboring carbon, and technically we could shift one of them over here to the carbocation, and we'll get a result that looks like this. But in this case, it's not any better than the original because this original carbocation is on a secondary carbon, and this is also a secondary carbon. And these methyl groups are way too far because they're like two carbons removed from the original carbocation. And if you remember, we can only shift it if it's one carbon away. So this will not undergo rearrangement because there's no preference between either of these. It's the same stability. For the second carbocation, it's also not going to undergo rearrangement because it's already at the most stable it can be. Because if you see, all of these are secondary, whereas these two are tertiary. These carbons have 3 substituents, and so there's no way to go from a tertiary carbon up to like a quaternary carbon in this case. So there's no reason for it to rearrange because it's already the most stable position it could be. So this will also be Na. For the third carbocation, this one will rearrange because, as you can see, the original carbocation is a secondary carbocation, whereas this potential carbocation, which is only one carbon away, so it can shift. If the carbocation shifts over here, it'll be tertiary, which is more stable than a secondary carbocation. And in this case, since we have these two methyl groups that could be moved, but we also have a hydrogen, because remember that carbon wants to form 4 bonds, so you can draw in the hydrogen, and instead of moving the methyl groups over to the carbocation, we want to shift the hydrogen because it's lighter and therefore it's easier to move. Because think about it, when you're moving to another place, it's easier to carry a lighter box than a heavier box. So in these cases, if you're given the choice between shifting a methyl group or a hydrogen, you always want to shift the hydrogen. So in this case, this hydrogen will shift over here, and you will get a new carbocation that looks like this, where it's tertiary and more stable than the original secondary carbocation. In a similar fashion, the last carbocation will also rearrange, and that's because it starts off as a secondary carbocation, but as you can see, this neighboring carbon has a potential to become a tertiary carbocation. And similarly, since carbon has 4 bonds, we need to draw in this hydrogen, and since it's easier to move the hydrogen, which is lighter than the methyl group, we're going to shift the hydrogen over to the carbocation, and we're going to get a new carbocation that rearranges like this. 9. Are hydrohalogenation reactions stereoselective? Why is this the case? Your answer should include structures and should not exceed 2 sentences. So for this, since we're asked to provide both structures and sentences, we can just choose whichever alkene we want. To keep it simple, I'm just gonna draw in this molecule, and we're gonna react it with hydrogen bonded to bromine. And as always, the alkene acts like the nucleophile. It attacks the hydrogen and breaks the bond. So there's going to be a leaving group. The bromine becomes the negative leaving group, and you get an intermediate that looks like this with the leaving group, which is negative. And in this case, there's no other intermediate steps, and this negative bromine ion is just going to attack the carbocation, and you're going to get something like this. This is non-stereoselective because this carbocation is 3D, and there's no hindrance from either side of it because there's nothing blocking the way of the bromine ion to attack it. So it's going to attack both sides of it equally. So you'll get something like this and this, but it doesn't really matter how you draw it. So, for the justification, I would just say that the carbocation has both top and bottom side unhindered. So the bromine ion has no preference on which side to attack. And we just have to conclude that it's non-stereoselective. And which of the following alkenes can produce 1-chloro-1-ethyl cyclopentane when reacted with hydrochloric acid? Indicate all that apply. So for this problem, it's basically asking us which one of these starting materials will end up with a carbocation that looks like this, to which the negative chlorine ion that comes from breaking apart this bond will attack. So we're looking for carbocation formation and rearrangement. So let's start with A. As we remember, the alkene will try to grab the hydrogen atom, and then this chlorine will leave, and we'll get something like this, where the carbocation can either form on either end of the alkene, the double bond. And in this case, it's going to try to form here in this this carbon, because this carbon is more substituted, it's secondary carbon, whereas this carbon is primary carbon. But as you can see, it can be further rearranged, and I'm just going to move this a little bit. It can be further rearranged because this nearby carbon is tertiary, whereas this original carbocation is secondary. And remember that it's easier to move a smaller box than a larger box, and since carbon has 4 bonds, there is a hydrogen atom that's bonded to this carbon, this tertiary carbon, and it's going to shift over to this carbocation, and we're going to get something that looks like this, with the carbocation shifted to this tertiary carbon. And this matches up with this goal product, this goal intermediate of the carbocation that we want for successful synthesis of this molecule. So A will be one of our successful starting materials. For starting material B, a similar thing happens. This double bond is going to grab the hydrogen, and the chlorine will disassociate from the bond, and we'll have an intermediate carbocation that's either going to be on this carbon or this carbon. Basically, it's on either end of the alkene or the double bond. In this case, we don't really have to rearrange anything, because as you can see, there's 2 possible places the carbocation can end up. Since this double bond is between this carbon and this carbon is secondary, whereas this one is tertiary, and it's going to form at the tertiary carbon because it's more stable. And this again matches up with what we want, so B will also be a successful starting material. For C, we're just going to do the same thing again. In this case, the double bond also grabs onto the hydrogen, the chlorine leaves, and we'll have carbocation intermediate that's either going to be here or here. And because this one is secondary carbon and this is a tertiary carbon, it's going to form at the tertiary carbon. And we don't need to do any further rearrangements. And as you can see, these also match up to the carbocation intermediate that we want for this product to be made. So C is also a successful starting material. Now let's continue with D. Same thing happens. The double bond will grab the hydrogen, and then the chlorine will disassociate from the bond, and we're going to get something like this, where the carbocation intermediate can be either of these carbons, and it doesn't really matter, but since the goal is to have it on this carbon, I'm just going to put the intermediate carbocation here. And the reason why it can be either of these is because both of these are secondary carbons, so there's no preference for either of them. They're both equally stable as carbocations. But in this case, we can shift the carbocation and it can rearrange. And I'm just going to move this over, because this is a tertiary carbon, whereas this carbocation is a secondary carbocation, and it can be more stable if it's moved to this tertiary carbon. And there is a hydrogen that's not shown because it's a carbon skeleton structure, but it's there, and it's going to shift over here, and we're going to get something like this, which matches with the goal carbocation that will produce the successful, it's going to be successful in making this product that we want. So yes, D is also a successful starting material. I'm going to make all of this smaller again, and we'll look at the last one. For E, we're going to go down the same path of the alkene is going to grab the hydrogen and the chlorine is going to leave. And in this case, similar to D, we can either place the carbocation here or here, since both of these carbons are secondary carbons. So they're equally stable in terms of carbocation placement. And it doesn't really matter, so I'm just going to put it on the right side. And as you can see, the ideal that we want is for the carbocation to end up here. But we can't do that because remember that hydrogen and methyl shifts can only do it, you can only shift it one carbon to the left or one carbon to the right. In this case, there's two in between, so this can't rearrange, and there's no way we can get this ideal carbocation intermediate that will lead to this product. So all of these are successful starting materials except for E. Bonus question 1. Provide the major product for the reaction shown below. For this problem, it's just the same thing as the previous problem, where this alkene, this double bond, is going to grab the hydrogen, the bromine will leave the bond, and we'll have some sort of intermediate that looks like this, where the carbocation is formed at this carbon and not at this carbon, because remember that carbocations can be formed at either side of the double bond, but this carbon is preferable over this one because this middle carbon is a secondary carbon, and this one on the end is primary, and the secondary carbon is more stable as a carbocation. And in this case, since it's a four-membered ring, it's cyclobutane, it's gonna, this bond is gonna shift over to this carbocation to form a five-membered ring to make it more stable. And this only works for 4 to 5 or 5 to 6, but it doesn't go up from 6 to 7. And that's something you need to remember for these types of problems. And now we can, there's also the bromine is a negative ion that just leaves the bond. In this case, now we can bring back the bromine, and the negative bromine is going to be attracted to this carbocation, and we're going to have a product that looks like this. And we can just box this. We don't have to draw the stereochemistry or the different products, because technically there are two ways that you can draw it. You can either draw it this way or this way, because this carbocation, it's 3D, and there's nothing hindering the bromine, the negative bromine ion from attaching from either side of it, so it can attach from the back or from the front. But since we're not given the stereochemistry of this methyl group, we don't really need to draw it, both products, but you should keep in mind that they are racemic. There's no preference of one over the other. Bonus question 2. In a similar fashion to chloronium ions, protonated epoxides react with nucleophiles. Based on this analogy, draw the product of Cl- attacking the protonated epoxide below, carefully depicting stereochemistry where appropriate. So, since we know that it's going to act similar to chloronium ions, we can kind of predict this mechanism. And in this case, this chlorine ion can attack either this carbon or this carbon to break one of these dashed bonds to the oxygen. And in this case, it's going to want to attack this carbon because this carbon is more substituted and therefore has a greater partial positive charge. So it's going to attack from the other side, and then this bond between the carbon and the oxygen is going to break. We'll have a product that looks like this, with the broken bond is going to push all this alcohol group to this side, and then we're going to have inverted stereochemistry where the chlorine is going to be wedged. It's going to be wedged rather than dashed, because keep in mind that this whole top side of this molecule is blocked off by this protonated epoxide. So this chlorine ion has no choice but to attack from the bottom side. And that's why we have a wedge instead of a dash. And you have to keep in mind that in these cases, it will just be an inverted stereochemistry. Bonus question 3. You are a chemical engineer working at a petroleum refinery developing distillation processes that can separate different alkenes and are trying to identify the alkenes in different distillation fractions. Based on the chemical analysis you have done so far, you have determined that 3 fractions, A, B, and C, are each one of the following alkenes. Due to being isomers, they behave the same in most tests that are available until you perform combustion calorimetry. In this experiment, you determine the enthalpy of combustion of each fraction. Which alkene is in which fraction? So for this problem, we're given 3 alkenes which match up to 3 different fractions. And so I think the best way to approach this problem is to first rank the stability of these alkenes in order, and then the stability of the fractions in order. So let's look at the alkenes first. Since they're all isomers and they're all like the same molecular weight due to the definition of being isomers, but they only have, all of these alkenes just have one double bond. So I'm guessing that the first thing you might think of is E and Z configuration, and that would be correct. So looking for E and Z configuration, you can start from the left and go to the right. In this first alkene, you can see that these are hydrogens that are just not drawn, but the higher priority groups are on opposite sides of this alkene. So this is going to be E configuration. And I'll just write trans. Actually, never mind. For the second alkene, we can do the same process, and we know that there's 2 hydrogens bonded to each side of this double bond as well. And we know that these 2 high priority groups are on the same side, and that would be Z, which is the same side configuration. For the third alkene, this can't be assigned E or Z configuration because one of these sides has 2 of the same groups. It has 2 hydrogens, and one of these hydrogens is not greater priority or greater molecular weight than the other, so this has no E or Z configuration. And if you remember, in terms of stability, it goes from most stable being E, and then Z, and then the least stable is no E or Z configuration. So in this case, we can order it as 1 is more stable than 2, which is more stable than 3. And now we should do the same thing with the fractions and this data that we're given. This delta H means the change in enthalpy from the start to the end of the reaction. And as you can see, these are all negative, which means that these are all exothermic reactions. So rather than looking for the sign of the reaction, we're just looking for the magnitude. And we want to look for, to see the most stable fraction. The most stable fraction will have the smallest magnitude of heat released because it's going to be the most stable. And then in contrast, the least stable will have the most heat released, so the greatest magnitude. So let's just get rid of these negative signs for now, and let's apply the similar logic to these fractions. So in this case, we can see that fraction B has the highest magnitude, so that's going to be the least stable. And the next highest magnitude is fraction A, which is 1277.9 kcals per mole. So that's going to be the intermediate stability. And then we have fraction C left as the most stable. And now we can just kind of match these up with what we found earlier with the stability of the alkenes and just write our answer. So for fraction A, we know this is 2, and fraction B, we know it's 3. Fraction c is 1.